Okay, Miss Howard's Chemistry. This is the last set of last video for the nuclear chemistry notes. We're still talking about nuclear chemistry. We're mainly focused on C12C, compare fission and fusion reactions. Okay, so first of all, letter E, your nuclear equations. You have homework. We talked about that before you left for spring break, so you need to make sure you do that. We did samples, and all you need to do is continue what we did in class. Now, letter F on your notes is the half-life. And a half-life is the time required for half of the atoms in a radioactive substance to decay into something else. Okay? It may be a totally new type of atom, or it may be a different isotope of from what you started with. So the half-life, letter F, is the time required for half the atoms of a radioactive substance to decay. And the shorter the half-life is typically a less stable atom. So some isotopes have half-lives of thousands of years, and some of them have half-lives of a few seconds. So the shorter half-lives indicate that it's a less stable atom that we're dealing with. Okay, so you need to know the difference between fission and fusion, and it's really pretty straightforward and simple. Fission is when you split the atom. It means it's going to make a smaller nuclei. You might have two, like in the picture below, you've got two, the krypton and the barium nuclei that are formed, and then you also have some, do you see the neutrons that are coming off of there? You also have some neutrons that are coming off of that. So when you split the nucleus, what you have is a fission process, and you have lots and lots and lots of energy that's released with this. This is what, when we talk about nuclear weapons, we're talking about fission. All the energy released from that comes from the nuclear binding energy inside the atoms. All that energy that you can blow stuff up with, that's where it comes from. It comes from the internal parts of the nucleus. Okay, so 1 gram of uranium-235 releases the same amount of energy as burning 3 tons of coal. That is absolutely amazing. Again, think of a gram like one of those big paper clips. So that's it. 1 gram of uranium-235 releases the same amount of energy as burning 3 tons of coal. That's just wow. Okay, a chain reaction is when it's self-propagating. That means once you start it, it continues on its own. Once you put enough energy into it for it to start, it continues on its own. So when you have that nuclear weapon, you have the energy that you put into it, and then it's going to continue until the material's gone. It has to have a critical mass of the material to sustain the chain reaction. So that's what they talk about in the nuclear weapon. There's a certain amount of the nuclear material that has to be there, and they're separated until you're ready for the bomb to blast, and then you basically have some type of explosive, and that smushes them together to make one mass, and that's your critical mass for it to work. Okay, fusion is different. Fusion is actually more common in the universe, not on the planet here, but in the universe, because all the stars run and are basically fusion explosions. So fusion is when you combine 2 nuclei to form one nucleus of a larger mass, like 2 hydrogen nuclei fused to form a helium. That's what would be happening in the sun. So the thermonuclear reaction, oh my gosh, this requires temperatures of really, really high amounts to sustain. Hence, stars, the sun, that's where it's happening. Okay, so 1 gram of fusion fuel is worth the same amount of energy as 20 tons of coal. So fusion, you're getting much more bang for your buck as compared to the fission. And it occurs naturally in the stars. This is what's happening. So if you look down below at the bottom, you have hydrogen and a hydrogen atom, and you're not just forming H2. What you're doing is you're fusing them into one atom, so that you have a new substance created. That new substance is not just, a chemical rearrangement of atoms, it's actually helium that's being produced. Okay, so fusion versus fission, and I don't know if I put this page on your notes or not. Oh, I did! There's a pretty picture on your notes for this. So we have 2 pictures, fusion versus fission. With fission, uranium-235 is limited. So you have a specific amount. You have to worry about the danger of a meltdown. You have to worry about toxic waste that you have to deal with. And then you also have to worry about thermal pollution, because when you're dealing with fission, like in nuclear reactors, there's a lot of heat generated, and so they can take, let's say, water from a lake, and they can run it through the system to cool it down, and when the water's put back out of the system, instead of being cold water, it's hot water, and so we call that thermal pollution there. So we're not talking, in this case fission, we're not necessarily talking about a nuclear weapon, we're talking about maybe like nuclear energy. In fusion, you have an abundant amount of fuel. So with fission, you have the amount of uranium on the planet is pretty limited. With fusion, you're talking stars and suns, and so you have this massive, massive, massive amount of fuel that you could do that. So that's why a lot of people are trying to develop fusion reactors so that you can have this tremendous amount of energy, and you use hydrogen as your fuel. In fusion, you don't have to worry about a meltdown. There's really no toxic waste because it forms helium. I mean, that's about it. The problem is it's not sustainable here on our planet. We can't get it to be quite sustainable for us yet. So we have fusion and fission. And we are finally finished with this set. So now you can go through and make sure you have all of the packet finished, because remember, the last page in your packet will be for a grade, and then the whole rest of the packet filled out is a test grade. Have a nice, enjoyable spring break.